So today we have Niall speaking on unitary calculus with reality.
All right, thank you. Thanks to Sarah for the invite to speak. So I want to try and talk today about a particular type of calculus functors on a very particular category. I'm going to come at it from a homotopy theory point of view. So I'm going to essentially skip the entire construction, but talk about how we can think of this calculus through some model categories, and how we can kind of do the standard thing where you classify the layers of Taylor towers, but use model categories to do it. So if you don't really care about calculus of functors, you could think of this talk as an example of when localizations of model categories can be useful, and how sometimes when you localize things and you expect it to be kind of nasty, you actually end up with something which is quite nice. So today's talk is going to focus on one particular category of functors. So I want to look at functors from what I'm going to write vector spaces over C, but with a very particular C2 action to C2 spaces. So spaces of the C2 action. So this category of vector spaces, let me be a little bit more precise about what I mean. So I want the objects to just be finite dimensional inner product subspaces of C infinity, the morphisms to be linear isometries, and I want the C2 enrichment to come in the following form. So take some element of C2, a linear isometry, and on a vector space V, what I want to do is, on a vector V, I want to take the complex conjugate of the vector, then apply F to this, and take the complex conjugate again. And let's say F is some linear isometry V to W, and this case G is the non-identity element of C2. So in the case it's the identity element, it doesn't actually do anything. So this is really complex vector spaces, but you remember the fact that complex vector spaces have a complex conjugation. You're just taking an enrichment with respect to that complex conjugation. So then how does the calculus work? Well, it works just like any other functor calculus. You start off with the functor you care about, and you assign to it a sequence of polynomial approximations which build up to a tower. And the thing about this tower is that it sits under F, so it's an approximation to F, and we want to use this tower, these polynomial approximations, to gain some insight on the original functor F. And kind of the way that we understand any kind of tower is by looking at the layers of it, or the homotopy fibers of the maps in the tower. So we take the homotopy fiber at each stage, we get these things that we'll label with D1, D2, etc. And we want to use information about these layers to tell us something about the entire tower and try and kind of figure something out about the functor F that we started with. So the kind of point is that the nth approximation is the universal n polynomial object under F. So what does this mean? Well, if you have a map, say F to E, so an enriched natural transformation, but I'll just call them maps, where this E is also n polynomial, then this map will factor through the polynomial approximation of F. But importantly, this is only up to homotopy. And kind of one of the goals of this model category approach is to get rid of this up to homotopy phrase and have some kind of understanding as to what we actually mean by this. So the other thing to know about the tower is that the nth layer, so this is the homotopy fiber of the map from the nth approximation the n minus first, so it's kind of the error between these two things. This has two important properties. So first of all, it is n polynomial. So something that's n minus 1 polynomial is n polynomial. So n minus first polynomial approximation is n polynomial. And if you take the whole fiber of a map between polynomial things, you end up with a polynomial thing. And even more, it has trivial n minus first approximation. And when these two things happen together, we say that it is n homogeneous. So our model category considerations boil down to finding some kind of model structure that tells us about the nth approximations and finding one that tells us about the n homogeneous functors. So let's see how we can build these. So let's start off with the projective model structure. So everyone's favorite model structure on the category of functors. Let me go back up and copy this because I will be using it a bunch. Okay, so just in case anyone's never seen this, so the weak equivalences here are maps of functors that when you look at it on each level, so at each vector space, the induced map is a weak homotopy equivalence. So I should point out that I mean weak homotopy equivalence and not on fixed points. So there are no fixed points happening anywhere here. I'm just taking the underlying equivalence of these things as spaces rather than C2 spaces. And the fibrations are then just, again, the level-wise fibrations. So this map on at V if you want to be a stereo fibration, and again, no fixed points anywhere. Okay, so this model structure has all the properties you would ever want a model structure to have, which means we can do various localizations to it. And one thing I'm going to do is I'm going to localize at the functor Tn. So this is a very particular type of localization. So the thing to note is that you can think of the polynomial approximations as a functor, and it's an endofunctor on the category of functors that we care about. So it sends a functor to its polynomial approximation. So we can what's called Biesfeld-Friedlander localize at this endofunctor. And the result is a model structure that will tell us about the n polynomial objects. I should say that you can do other similar things in other versions of calculus. This is not unique to this situation. So there is a model structure on, again, this category. And I only need to tell you what the weak equivalences and vibrations are. Everything else follows. So you take, again, maps, functors, but the asset there then a levelwise weak equivalence on their polynomial approximations. So the induced map is a weak equivalence. So vibrations are then maps. Well, first of all, you want, at each level, you want to get a fibration. Let me just put a double-headed arrow. And you want a pullback condition. So if you have the square formed by polynomial approximating, and you want this to be a homotopy pullback. So sitting inside these weak equivalences are kind of all the information you would want to know about polynomial approximations. And sitting as the fibrant objects are exactly the n polynomial functors. So to see this, you really need to see that this Biesfeld-Friedlander localization is actually just a left Biesfeld localization. But you can kind of see why it should be true. So if you take something fibrant, then the map to the initial or to the terminal functor is a vibration. So what that gives you from above is that, first of all, you have vibration spaces, but importantly, it's the following condition. So when you look at this pullback square, you get a square that looks like this. We have vibration and weak equivalence, and pulling that back always gives you, or not always, but in a right proper model category gives you a weak equivalence. So we get that f and its polynomial approximation are equivalent. So here we have everything you'd want to know about polynomial objects sitting inside one very nice, very easy to construct model category. But it doesn't actually tell us anything then about the layers of the tower, right? So we want to kind of do something to this model structure to find out more about the layers. And so to do that, what we're actually doing is we actually write Biesfeld localize this, which if you know much about Biesfeld localizations, you probably think is some sort of sin, but we'll see that it actually comes with a nice description.
What's the relation between fibrant objects and polynomial functors?
You're fibrant precisely if you're n polynomial.
Okay. Okay.
So let's look at this one for the layers. So again, we're still thinking about our category. We should just copy this entire phrase. On this thing with, well, the weak equivalences are exactly what they want them to be. So they are maps, and you have that the nth layer of the tower between these things agrees. So again, you can think of this dn as an endofunctor, and you just want that the nth layer of the tower for E and the nth layer for the tower of F agree.
Does this stuff actually depend on like the very specific kind of functor category you chose?
So to get to see that fibrant things are n polynomial before, you need to have a very particular set of maps to localize that, and that depends on the functor category. So essentially what happens is that you construct this horrible homotopy colimit of these Stiefel manifolds built out of these vector spaces, and that turns out to be actually homeomorphic to a sphere bundle of a particular vector bundle, and without that, none of it works.
All right, thanks.
Okay, so it does n come into the does n come in because of like the vect n, or where?
So I mean, you get one of these for every n.
Oh, every n, okay.
Yeah, so I mean, you essentially replace the tower with a tower of model structures that tell you information about each individual part of the tower.
Okay.
So the fibrations of this model structure are exactly the ones for the n polynomial model structure before. So if you know much about model categories, this tells you exactly how we got this. It's the right bias-free localization. But what's interesting here is that the cofibrations, or well, the cofibrant objects, are those F such that they have trivial n-first approximation, which tells you in particular that if you take something that's cofibrant and fibrant, that all these are exactly the n-homogeneous functors. So the point that we care about is that dn of f is always in the cofibrant fibrant objects for any f. And this gives us some method of actually trying to calculate what these things are. So again, this is a right localization of a left localized model structure. So this should all be pretty surprising. You should never expect the right localization of a left localization to be anything nice. But you end up with a model structure that is relatively nice to describe. And Kemp's, the rest of this talk is to try and characterize this model structure by something more familiar to most people. So to see what, well, I should say are there any questions here before I move on. All right, if not, we will move on. And I'm actually going to take kind of a sidestep away from this calculus and go to Goodwillie calculus for a moment. So that's what most people are probably familiar with. So in Goodwillie calculus, you get a similar picture. So the theorem I want to tell you about is due to a bunch of different people at a bunch of different times in a bunch of different ways. So the kind of basis is, well, due to Goodwillie, unsurprisingly. But there are versions of it by Biederman, Chorney, Rundigs, other version by Chorney, Rundigs, and a version by Barnes Eldred. All of whom considered slightly different characterizations of Goodwillie calculus. But nonetheless, they all said that n-homogeneous functors, so in particular the layers of the tire, but up to homotopy is the same thing as looking at the homotopy theory of symmetric spectra, or with spectra with an action of the symmetric group or the n-symmetric group. So in particular, this comes in the form everyone is probably familiar with. You take some functor, say from base spaces to base spaces, and you get that the nth layer star at some space x is, well, it's an infinite loop space of the derivatives smashed with a bunch of copies of your space, and then you mod out by the sigma n action. So kind of the rest of my talk is going to be, well, does something similar happen here? Can we characterize homogeneous functors by spectra with some kind of group action, and do we get a nice infinite loop space coming out as the layers? So the very first thing, going back to the calculus we're looking at, if you take some functor in here, well, then you can differentiate it. You can build this derivative, and it would take too long to explain how you build this derivative. It's essentially an exercise in category theory. It comes as a right Kant extension. But the nth derivative of f, which I'm going to call this, or denote by this is the nth derivative. This is it before it becomes a spectrum. It's actually a module over the n sphere functor. So this is the functor which sends a vector space to the one-point compactification of n copies of the vector space. So what that means is that there are structure maps that look something like this. So the nth derivative of v gets suspended a bunch of times, and you go to the nth derivative of v plus w. Plus some equivariance that, again, it would take too long to be precise about the equivariance happening here. But the point is that this category of modules over the n sphere is basically spectra, right? Spectra is modules over the sphere. We just have an n where we want to 1. So this moderately reduces to how do we get rid of the n? So just as there are model structures on spectra, you get a model structure on modules over this n sphere, right? So this category has a stable model structure. And it's actually relatively easy to describe. So if you think about kind of this category and some nice model for spectra, well, a nice model is one in which the weak equivalences are detected by pi star isomorphisms, so not symmetric spectra. All you do is take the pi star isomorphisms here, which are defined by taking a colimit over the structure maps, and you take a colimit over the structure maps in this module category, so you have an n pi star isomorphism. Just keep track of the fact there's an n happening in the suspension. And again, the kind of obvious things happen. If you take an omega spectrum here, what it translates to is just what we call an n omega spectrum. To define kind of, you just have to take the adjoint structure maps to be weak equivalences, and this gives you a nice stable model structure on this category. And in fact, this method of taking the derivative turns out to be a right equivalent functor. So more precisely, this is kind of the hardest part of the entire thing. And actually we'll use, the proof of this uses some of the later kind of things we'll talk about. So start off with a functor, you take its derivative, you end up in this category of modules, and this is a right adjoint. And when you consider the n homogeneous model structure here, so this is the n, anytime I put an n here, I mean the n homogeneous model structure. And this is the one where the weak equivalences are detected by the layers. This adjoint pair is equivalent equivalence. A equivalent equivalence. So I mean, if you're happy enough with replacing having to compute single loop spaces by computing n-fold loop spaces, you're done, right? You have homogeneous functors are spectra up to homo W. But we still want something better. We want to really land in some kind of actual category of spectra with a group action, and we're not there yet. So are there any questions at this point before I transition?
No, I just thought the interaction between like the sigma n and like the vect n was interesting. Like I don't know, like interaction between sigma n and gln maybe.
I'm not sure I quite understand the question.
Neither do I, but yeah, I mean, I'll ask at the end.
Ari's been on representation theory, and so now he sees sigma n's and GLNs as the same thing.
Okay, well, let's pretend they're not the same thing. And so I can spoil it a little bit for you. Here we have a sigma n. You'll end up with in this calculus, you'll end up with well, it'll be a completely different group. But it is the semi-direct product of C2 with UN, if you really want the full spoiler. So anyway, let's try and get rid of this n in this modules category because it's irritating. And so everything we've done has this built-in C2 action by complex conjugation. So kind of the natural point or place to look is at some kind of spectra that has an action by complex conjugation built into it. And this is exactly what happens in what is called real spectra, and the version of which I'm going to give is due to Schwede in his lecture on equivariant stable homotopy theory notes. So a real spectrum well, it is, first of all, it's a sequence of spaces. But you ask that the semi-direct product of C2 with UK acts on the space YK. You have structure maps S2 to YK plus 1. Here the S2 is showing up because this is exactly the 1-point compactification of C. And then you ask that the iterated structure maps are suitably equivariant, so C2 semi-direct, then the product UK UL equivariant. Here we're just letting C2 act on these unitary groups by complex conjugation of the matrices, so term-wise. Right, and kind of the reason why anyone cares about real spectra is that there is a very useful example. So the spectrum mu, so this is given by mun, which is the classifying space of the tautological bundle over bun. So it looks like EUN plus smashed over UN with S and C. This thing is actually commutative real ring spectrum. And kind of the point is that this is kind of the structure that mu comes with built in, but we always like to work in some kind of model of spectra that's more familiar to people, so you want to change it to orthogonal spectra. And Schwede tells you exactly how to do that. So you take some y in this category of real spectra, so I'll just put an or there to remind us. And you get an orthogonal spectrum, which is called phi y. And at level n, this is just, you take base maps from the 1-point compactification of the imaginary axis to your spectrum or your real spectrum. And this turns out to be an orthogonal spectrum. And well, does it actually do anything useful? You take phi of cobordism spectrum and you get the real cobordism spectrum. So this is the spectrum that has non-equivariant homotopy type. It's just that of mu, and geometric C2 fixed points recover the unorientated cobordism spectrum. So we can kind of take what Schwede did and run with it a bit. And what you end up with getting is the following. So this this phi turns out to be a functor, right? This is all functorial. So we can relate orthogonal spectra in these real spectra. So if you take category of real spectra, add on a UN action. So this is what's sometimes called naive UN spectra, but spectra with an action, so it makes it more clear what it actually is. Then phi is a functor from this category to the orthogonal spectra with an action of C2 semi-direct. UN, it has a left joint which you can cook up. And in fact, so both of these are categories of spectra. You take their underlying model structure. So you just look at pi star isomorphisms. Again, no fixed points in sight anywhere. And this is equivalent equivalence. So we're kind of there in a way, right? We have this category of spectra or orthogonal spectra with an action, but we're just missing kind of one connecting step. So what happens if we try and take a look at the picture so far?
Can you remind me what the SPR and SP theta is?
So the theta is supposed to be a curly O. This is
Okay.
orthogonal spectra.
Okay.
Right, so ignoring the brackets, you just take orthogonal spectra.
Mm-hmm.
Then you just ask for this to come with an action of C2 semi-direct UN.
Mm-hmm.
So each of the levels, so each of the spaces has an action, but you leave this suspension coordinate free.
Mm-hmm.
The one with the OR is just this real spectra of theta,
Mm-hmm.
but then you add on an external UN action again.
Thanks.
So what is the picture? So we started off with our good old category, and we thought, okay, take the n-homogeneous model structure or the homogeneous functors up to homotopy. And we saw that differentiation gives us a module over the n sphere that's equivalent equivalence. Then what we saw is that the place we'd want to end up is probably orthogonal spectra with the C2 semi-direct UN action. And we saw that is real spectra with a UN action via this functor of Schweda, and the gap is this. Questions about what happens in here. So the first thing, if you stare at this category of real spectra for so long, you see that it is exactly a particular category of modules over the sphere where this is, again, you send a vector space to its one-point compactification. And the point is, kind of this part, we're using complex vector spaces, and here we're using real. So we mean modules over the complex spheres. So now the question is, well, how do you go from a module over a sphere to a module over an n sphere? And well, you just multiply by n, right? So we can find a functor that we call alpha n upper star from modules over the sphere and modules over the n sphere. All you're doing is term-wise multiplication by n. So alpha n star at some module over the sphere, some complex vector space V is just x at n times V. And this has structure maps, kind of the obvious thing. Well, obviously if you stared at it for long enough. This at V smash SNC, well, you read it out, you get X NV smash SNC. And then you just keep doing the structure map of F as X as a module over the sphere. and you get x at mv plus nc, which is exactly what you wanted. So this alpha n upper star actually really tells you what's going on, but again, I'm sweeping a lot of the details under the rug. So what's really happening is that these categories of modules are diagram categories, right? So they're both indexed on some small category, and the alpha n is actually a functor between these indexing categories that is just multiplying v to nv, and you take precomposition of that, which gives you the upper star. And in fact, this is a right equivalent functor. That's exactly what we wanted. Okay, so we had this category of modules over the n-sphere. We saw that there was a map in this direction. It is a right equivalent functor, and these are equivalent. So again, half the details are missing, and I'm kind of ignoring all the equivariance happening in the picture, but this is the basic idea. So if we go back to the picture, let me copy it down. We can then just fill in the gap with this alpha n. And this is exactly what we wanted. We take a functor and we produce a spectrum with an action of a group. But annoyingly, this is a zigzag of equivalences. But on the derived level, it doesn't really matter. So one interesting thing about the zigzag is that it's actually longer than the standard zigzags. So in the good calculus case, there is a similar zigzag between n homogeneous functors there and vector with an action of sigma n, and it's a two-step zigzag. This is a three-step zigzag, and that just comes from the fact you have the C2 equivariance underlying everything. So to get the spectrum, all you do is you just take a functor and take its derived image, and you get what we classically call theta fn, which is you should think of as the derivatives of a functor similar to the derivatives used in the classification in Goodwill calculus. So, are there any questions at this point? All right, so you might be thinking, okay, you have this classification, can you do anything with it? So let's take an example. If you put in our good old friend, the n-sphere, so this is the one that sends the vector space to the one-point compactification of n copies of the vector space. This turns out to be a compact object in this category. So it has to be sent by compact objects. So, okay, let me start over. This n-homogeneous model structure is stable and compactly generated. So if you have equivalence between two stable model structures that are both compactly generated, they have to send compact generators to compact generators. And so the whole way through this zigzag, this has to be sent to compact things. Each step, there is only one compact thing it can be sent to. So you get that spectrum at the end is the suspension spectrum of the unitary group, where you let C2 act on the unitary group by conjugation of the matrices. You can do some lower level ones. You can take the real classifying space, so you send a vector space to classifying space of its unitary group, but again, having that C2 action by a complex conjugation. And the first derivative, which is actually the only one I can calculate, is a shifted sphere spectrum down by 1 degree. And for the good-willy people in the audience, you take the sphere, so again you send a vector space to get 1-point compactification, and kind of heuristically, without giving any details, the derivatives for varying degrees are in some sense connected to the derivatives of the identity functor on spaces. So the final kind of point I want to make is that this actually tells us a lot about the Taylor tower. So you get the classification you would want. So you take a functor, which is homogeneous, and you get it in terms of spectra. So I'm essentially saying that the derived image of this thing is just what you would think. So dn of f on some vector space V is what? Well, you take the derived image, you suspend it a bunch of times, first based on the layer of the tower, then based on where you're evaluating it. Both components of the smash product have a UN action. You mod out by said UN action. You don't kill any C2 action because the left-hand side here has a C2 action, so there's no point. You kill the C2 action, this just wouldn't be true. And you take the zero space or infinite loops of the spectrum, where this spectrum is exactly in spectra with the C2 semi-direct UN action. Okay, so we have this characterization, and the kind of final thing I want to go through is going back to this n-sphere example and seeing what we can actually say about its complete tower because of these model categories. This is all going to be about the n-sphere. And so the first thing that we saw was that the derivatives as a spectrum is the suspension spectrum of the unitary group. So we can just plug that into the formula and get that the nth layer of the tower is the stabilization of a suspension of the unitary group So one other thing that you can see is that this functor, the n sphere, is built out of cell complexes, right? It's cofibrant in the projective model structure. So this is cofibrant in the projective model structure. And it's actually in the set of objects at which we localize that to get the n-homogeneous model structure. So we get that this is cofibrant in the n-homogeneous model structure, which in particular means that its n-minus first approximation disappears. So if you think about how this tower is built, you have the nth approximation, or the nth layer, as the fiber between the nth approximation and the n-minus first approximation. So this is trivial. So we get the description of the nth approximation just as this stabilization. But even better, you can kind of take this idea, and you can see that, in fact, that for quite a large k, depending on the size of n, this is trivial if k is smaller than n-1. So you get, if you want to build the tower of this thing, if we were to draw the picture, you have the functor you care about. You have all these polynomial approximations. And well, we see that all of these below a degree are trivial. And this is this stabilization. And you can even, still just playing around with these model categories a little bit, see that kind of thing I'll end with is that the tire of this functor converges again to the functor under some mild assumptions on the dimension of the vector space. So my kind of sales pitch for this entire thing was, you want to classify these homogeneous functors, you can do it model categorically, you get an equivalence with spectra with a group action, and these model categories actually give you some kind of insight into calculations that you wouldn't normally have. And I'll stop there.
Great. On behalf of everyone, I'd like to thank Niall. Are there any questions?
I have a question about like more part of the setup than the actual things you presented, but it's about the Schwer's real spectra. I was wondering if you had like some sort of like infinity categorical description of real spectra.
I do not, that I can think of. I assume what you can do is kind of construct it in the same way you would construct the infinity category of spectra by stabilizing loops. But I've never thought about how you'd actually do it.
Okay. Okay. Thanks.
I have a question.
Yep.
Can you say any more about this relation between, I forget what it was, I stepped away for a second, but you mentioned the derivatives of the identity and that you
Right,
can
yeah, so
relate them to something.
You take, let me get this right, this category of vector spaces, whatever functor you want, let's maybe forget the fact that it has a C2 action, and then take some functor in Goodwillie calculus, right? There should be a chain rule that tells you whatever a chain rule should tell you, that I can't do it off the top of my head. Oh yeah, the derivative of this should be the derivative of G times the derivative of F over some kind of twistedy product thing. So you know the way the chain rule works in Goodwillie calculus, it's basically the same, but this time you have an orthogonal sequence here rather than the symmetric sequence, and you're just going to have to take this into account. And taking G to be the identity functor gives this whole thing the structure of a module over the derivatives of the identity.
Sure.
But you already know that they're modules over the sphere. And what this, if you take F to be the sphere, what you get is that the derivatives of the sphere are the derivatives of the identity. Plus or minus some equivariance. So it works better in like the orthogonal calculus setup than it does here, but there's definitely some kind of connection between all of these things.
Cool.
Any other questions? Well, if not, I'd like to thank Niall again, and I'll go ahead and stop the recording.